Okay, we are moving on. Today we are doing 8M3 Lesson 4, the fundamental theorem of similarity. Today's lesson is got a proof involved. It's got some pretty powerful concepts involved. It's kind of the beginning of some more tricky, maybe more involved geometry. So just stick with me today. I'm going to show you a proof, a somewhat informal, somewhat formal proof of the fundamental theorem of similarity. But hang in there. The key is getting to that homework help at the end. Get through the first part, absorb it. It's powerful, it's involved, but the homework, once you get the concept and you can start to apply it, it gets very powerful. And again, we're kind of at the, while we're building a lot on 8M2 here, a lot of what we did last unit, and then applying those concepts and some of the stuff we've done in the last 3 lessons today. But just hang in there. I'll try and tie it together. I'll try to go through it kind of slowly, kind of remind you what we know and how we're going to put together about 5 different building blocks to prove this fundamental theorem of similarity, which is so cool. It is totally awesome. So, what was that? I don't know. Okay, let's cut over to the drawing pad. We're going to do most of our work today on the drawing pad. I have a few screenshots from GeoGebra, but we're not going to actually go to GeoGebra today. So let's start off though with a homework problem. So there's not a homework problem. This is from lesson 4, right? Lesson 4. But I think it's like exercise 1 in the book. So this is the first thing you started off today. And so we start off with the fact that OR is that R is dilated from center O using a scale factor of 3. So what does that mean? So if we use a scale factor of 3, we kind of took this thing and we made it bigger to this thing. So what did we do? And so similarly, you know, we took this thing and then we multiplied it by 3 to get that thing. That's how we dilated. Remember, we took our, you know, you took your rays, you took your lines here, and you just made them, you know, 3 times longer. So, in other words, if this is 2.3, from here to here, let's do this a little differently. So if this is, you know, if this was 2.3, then from the longer thing is just it's 3 times longer, right? That's how we do our dilations. So we used our ruler and we'd measure this and then we'd multiply it by 3 and do the long thing. So that's just 3 times 2.3. So the length is, right, if you know, do your math, you know, 2.3 times 3, you know, you get 6.9. Similarly, if this guy over here is 3.5, then this long guy is, you know, 10.5. It's 3 times 3.5, which is 5, you're on 10.5 centimeters. So let's box up our answers like we like to do, commit strongly to our answers, and we can, you know, lay down our happy cat for both of our answers. And now the interesting thing about this fundamental theory, there's nothing that we've done so far that has anything to do with the fundamental theorem of similarity, but I'm just going to draw some lines here. And I want to look at something. I'm going to erase, let's just erase some of these things that we've drawn in here. Oops. Put that back. Oh, well, I don't know. Let's get rid of these things. And what we're going to do now is we're going to look a little bit at the fundamental. Okay, let's just choose this guy. Okay, forget about the rest of this stuff. Let's move Happy Cat over here. We did some work. Okay, now the interesting thing about the fundamental theorem of similarity is notice that these two lines, what it's going to say, the fundamental theorem of similarity, is if I take 2 points like this and I dilate them using a given scale factor around the same center, that the lines that are resultant, the line segments that are resultant, which are RS, right? This is RS. And this is R prime, S prime. These must be parallel. Oh my goodness. They must be parallel, 1, and 2, that the length is the scale factor times the length of the original. The length of the dilated line segment. You know what? Let's just write this all over again. So if you want, just skip through the next 30 seconds. I'm going to rewrite this. I'm just going to rewrite this neater for you. That the length of the dilated line segment, in this case, R prime, S prime, is the length of the original line segment, RS, times the scale factor. Okay, pretty cool. Now, let's move on. And the second thing we're going to do, so again, this is the fundamental theorem of similarity. And again, the precondition, it says if you dilate 2 points R, comma S from center point O with scale factor R, then this is true. You know, RS to R, S, R prime, S prime. Okay, so that's our fundamental theorem of similarity. Now let's go about seeing if we can kind of just prove this thing with a little bit of sense here. So let's just see what we can do here. So let's say that we have used a dilation, and we're going to use, you know, just kind of use these parameters. So we've taken A and we've dilated it to form A prime, to create A prime, and then we've dilated B and we've created B prime, and we've used the center at O, and our scale factor is 3. Okay, so let's look at this and let's see what else is true. So let's just do this. Let's form our line segments, AB and A prime, B prime. Now, what I want to show you is that this is a triangle. I want to convince you of this. I want to convince you of this. Triangle OAB is a dilation of, if I dilate that, I will get triangle OA prime B prime. If I dilate it using center O and R equals 3, then I get this triangle. So let's watch how this happens, because if I start here, this is what I start with, then this is true. This is like kind of step 1, step A. And let's draw these triangles a little bit clearer for you to see. Let's draw one of them in blue. And kind of the other one in red. But the way we're going to do it is we're going to just kind of take it like this. I'm going to kind of go around the outside and show it to you like that. So we have 2 triangles. So maybe it's not so easy to see, but just imagine that I'll explain this as we go along. So remember, whenever we dilated a triangle, we would take, and if we use R equals 3, right? R equals 3. We would take our center point, or each point, and we'd take it from the center, and then we'd multiply it by our scale factor. So clearly, OA and OA prime. This is, if this, this is a certain length, call it X, then this thing, it must be 3 times X, because that's what I did. I made this one 3 times further out. You can measure that with a ruler and you can see that it's true. And similarly, if this one was Y, then this thing is 3 times Y. 3Y. It's 1 more Y and then 1 more Y. That's how I created these things. Okay? So we're just going to erase that for a second. Okay, and so I've dilated that, the vertex A, and I've dilated vertex B. Okay, now what if I dilate point O about itself? Well, point O is, if I dilate it by because O is on top of itself, if I dilate point O about point O 1 time, 2 times, 3 times, point O is always, or point O always remains in place when I dilate it about itself, right? If point O is in the center and point O is 0 points away from point O, then when I dilate it 3 times, O, the dilation of O is equal to O, regardless of whether R equals 0, or sorry, if R is 1, 2, 3, or 100, because 100 times no distance is itself. So the interesting thing is, if I dilate it, and we can go to GeoGebra just to see that this is true. This is kind of fun. So let's just make a triangle over here, a polygon. And you'll see how this works. So, whoops. I told you I wasn't going to go to GeoGebra, but I just love doing it. So now the interesting thing is, if I say dilate, let's make a slider here. The slider is going to be cool. We'll call it A. Okay, and there's our slider. And then let's make it have a min of 0.1 and a max of 100 increment of 0.1. There we go, using slider B. So now what we're going to do is we're going to say dilate. Use our dilation command, dilate from point. We're going to choose our triangle, and we're going to dilate about 0.0. Oh, well, let's just do it like this. Let's say dilate triangle poly 1, comma B, comma about 0.0. Oh, where did that thing go? We're going to poly 2 equals the dilation of poly 1, comma B, comma about 0.0. There we go. So there, notice that we take our triangle. Let's make this guy only go, this guy only go to, say, let's make him go to only up to like 5. It'll make it easier to see. So, right, if we dilate OCD, and if we dilate, right, that's a half. And as we dilate it up and down, notice that 0.0 doesn't change, just C and D. So if we double it, O to C prime is twice O to C, and O to D prime is twice O to D. If we make it 3 times bigger, O to C prime is 3 times bigger. See, 1, 2, 3, 4, 5, 6, whereas OC is 2. It's 3 times bigger because our dilation factor is 3. And OD prime is 9, and OD is 3. It's 3 times bigger. But point O prime never moves. So if you dilate a point about itself, it just stays in place. So I just wanted to show you that. So similarly, notice how we have our 2 triangles that are dilations of each other. And wow, notice it looks like C and D and C prime, D prime. Those are parallel. It looks like they stay parallel all the time. But why is that? Let's finish up our proof and see if we can see why that has to be true. Okay, so I've convinced you, hopefully, that triangle OAB is a dilation of of triangle OA prime B prime. This big triangle is a dilation of the small triangle. Okay, now step number 2. Step number 2. Is that remember that dilations maintain the same shape. Remember back to earlier in this unit, in lesson, I think it was 1 or 2, remember that dilations maintain shape. And what that means, and we told you this, and this was one of our things that we wrote down, is that means that angles are preserved. They're preserved. The angles are preserved. The angles, are the same. The angle measures. Angle measures are the same. Okay, so if the angle measures are the same, then let's draw in what must be true. Then if this small triangle, this blue triangle, is equal to this big red triangle, then this angle must be the same as this angle. And this angle, angle OBA, must be the same as angle OB prime A prime. Now we get a very interesting phenomenon, and we have to go back to the end of lesson 2 to learn this. So what we've said is okay, so this says that angle OAB, that's this one here, OAB, the one with the 1 slash through it, is congruent to angle OA prime B prime. So that these angles are congruent. And similarly, angle OBA is congruent to angle OB prime A prime. But we don't need to know that. We don't really need to know that to finish off our proof. So what I want to do now is we know that these angles are the same. Now, some of you can remember back to the end of the last unit and know what kind of angles these are. Now, wait, I'm gonna show you something kind of cool here. And I want you to pay close attention. We're going to extend this guy, this line like this. We're going to extend this line like this. And we're going to extend this line like this. Now, I want you to look specifically. I know this is getting involved, so just hang with me. I want you to look specifically at this and this intersection. And remember what we talked about, transversals. Okay, transversals, and look at those two intersections of lines. And I want you to tell me what kind of angles are these two angles. Angle, this angle and this angle. What kind of angles are those two angles? Just answer that. We're going to continue to take it kind of slow. And so the answer is that angle OAB and angle OA prime B prime are corresponding angles. Right? These are corresponding angles. They're on the same side of the transversal, and they're on the same side of the two lines that are cut by the transversal. And so now we're going to go, now just look at that for a second. And so now we're going to finish with D. And so the answer is A prime, B prime must be parallel to AB because corresponding angles are congruent. Right? Because these angles are the same and these two lines are cut by a transversal and they're corresponding angles, those lines must be parallel. So what we have proved is this. We have proved that if you dilate 2 points, P and Q, to P prime, Q prime, about center O with scale factor R, then PQ is parallel to P prime, Q prime. Very powerful. The other half, that A prime, B prime is the length of AB times the scale factor, is something that we gave you earlier in 8M3, and we're not going to prove that today. Okay, very cool, very powerful. Now we're going to move on, and we're going to go straight to homework help. So this is homework help, and we're just going to use the power. So this is going to be a lot simpler. Now this is cool because we just used the power of fundamental theorem of similarity to answer questions. So again, this is far easier. So here, A prime, so we're going to start with this. A prime is a dilation of A, and B prime, if we dilate B, we dilate to B prime, right? And that's what we're given. We start with that. So I want you to answer now. Before I tell you the answer, I want you to pause and try. Pause plus try to answer these questions about what is the scale factor for this dilation, which angles have the same measure, and how do you know, and which lines are parallel, and how do you know. So now pause and try and come back. Okay, now I assume you're back. Now let's find the scale factor for the dilation. Well, we can use either this side, or we can use this side, or we can use this side. It doesn't really matter to figure out our scale factor. Well, let's use the easy one, because I can tell you, you can tell me how long, this is. And from here to here, it's 2. Right? It's 1 unit, 2 units. And here and O to OA, this is 8 units. 1, 2, 3, 4, 5, 6, 7, 8. It's 8 units. So our scale factor is what? If we have to multiply this short side by what to get the long side? So our scale factor in this case is 4. We can also look at it. Let's write R equals 4 to be more clear about it. We could have also done this, because this is 1 block and this is 2 corner blocks, and then this is 1, 2 more, 2 more corners, 2 more corners. So we could have said that this is actually, two diagonals. This is 2 diagonals, 2 diags, and the whole thing is 8 diags. See, so you could have measured that and said, hey, well, that's also 8 times bigger, or 4 times bigger. Okay, so which angles have the same measure? Hey, let's do this. I'm going to tell you to go to answer question C first and say which lines are parallel, and how do you know? Well, I'm going to say that, well, AB is parallel to A prime, B prime. And the answer is not, it's not because they look parallel. That is not the answer. That's not a legitimate answer. The answer is because of the fundamental theorem of similarity. Right? I took two points and I scaled them by the same scale factor. Right? The keys are 2 points scaled by same scale factor about same point. I did these things, and so if you do those things, you will get these lines must be parallel. Now, which angles have the same measure, and how do you know? Well, I know that this angle and this angle have the same measure, and I know that they have the same measure because corresponding angles are congruent. When a transversal, and that's when a transversal cuts parallel lines, then corresponding angles are congruent. Similarly, because this line is parallel to this line, I know that these angles are congruent. So it's not just angle B or angle OA, it's angle OBA is congruent to angle OB prime A prime, but also angle OAB is congruent to angle OA prime B prime. So this deserves happy cat, happy cat, happy cat, happy cat. Very involved stuff that we did today. Very involved stuff. But we're going to build on this. We're going to build on this as we move forward. We're going to continue doing problems with similarity. We're going to continue to do problems where we take, parallel lines and we cut them, and we look at triangles that are, similar, big ones. We're going to make them big, and then small, shrink them, grow them, make sure that we understand why these triangles have parallel lines, why angles are equivalent, and then start to do some powerful stuff with understanding, finding various angle sizes, cross shapes, do mathematics to figure out which sizes must be what if other sides are various lengths. It becomes very, very fun. It just becomes a big puzzle, and I like to put it together, and I like to try to teach it. I know this lesson is a little bit trickier because when you have a very involved proof that involves lots of building blocks, you have to slow down and understand each point. And if you have any questions, feel free to ask me questions. Send me an email. I've given my email out before, cowboy.lipscomb@gmail.com, cowboy.lipscomb@gmail.com, or just ask me a question inside the comments like some of you have done before, and I'd be happy to answer them, or make any clarifications or make additional videos to try and make this more clear for you. So thank you. I enjoy doing it. I'll be back for lesson 5 soon.